Now we're going to talk about an ambiguous case for the law of sines. So if you were given a situation where you had an angle, say B, given to you, so we have this angle measure here given to us, and then we are given a side length, right there, A, meaning this whole length here is A long, that wouldn't get us close to what we need to find. We'd then need some other third side. So if this third side were some side that was, say, coming from here to here, then we'd be looking at what is called the side-side angle case. And the reason we'd be looking at that is because we have a side right here, side, then another side, and then the angle. So the problem with this is it can create a confusing situation. Specifically, there are several different cases about what may happen with this triangle. So, worst case is that we don't have a triangle at all. Meaning, if we were to pick a side length where the length itself was less than the distance, meaning if we were to put that there, this would not complete a triangle at all. Problem. Okay, what if we actually have a triangle? Well, there's a couple different ways to go here. Now, one possible case is if we look at the perpendicular distance between this endpoint and this extension. Now, this opposite side is not necessarily this length, but it would certainly extend along that. Let's say that that side length was given to us as this distance here, such that this is a right angle. What does that create? It creates a right triangle. So that being a right triangle, it means that we can calculate its exact length. And we don't even need the law of sines. We know that h, which is what we'll call this because it's a height, because it's measured as a perpendicular distance, is equal to a sine b. So that is a value where we get one and exactly one possible triangle. Now it does mean that there are other side lengths that could be possible. Now one side length that is possible, it may seem trivial, but it certainly is that instead of having h, which would be certainly 1, not very interesting because it doesn't require even the law of sines. Another possibility is that we could be given the same length. That is, this side length here could be equal to a. If that's the case, what do we get? We get an isosceles triangle, which means that the length, the measure of this angle is also b, and then we can calculate this. And we then had to use the law of sines to figure out this, but that is certainly one factor. So what happens if a side length is somewhere between h and a? So what we end up with is somewhere between the situation where we've got this single triangle that's a right triangle, and then some triangle that's an isosceles triangle that's a. We could have some other length. For instance, this length right here. So we could have this length here that is, I think you would agree, between those two lengths. Here's the problem. That would mean we get a triangle here. So involving these two. And that would mean that this side right here, so this would be the angle A actually. So the angle A would be right here. So we have this triangle. That would have something. We could use the law of sines to figure out what that angle measure is, because we know that this measure right here would be little b, and it had to be given to us, and that'd be side-side angle. So here's where the problem comes in. This is one possible triangle. What if we took and we drew this same length in, but we drew it in at a slightly different angle? That is, what if we drew the triangle like this? That would mean that this length is still b, and this length would still be a, because it's opposite little a, but the problem is this triangle and this triangle, I think you'd agree, are, well, entirely different. So here's the question. How can we figure out what these different cases are? Well, first off, we have a limiting factor. That b, if it's more than the h, so if b is more than the h, but at the same time less than the a, that's the situation. So if we end up with a situation where B is greater than H, but at the same time less than A, so greater than H but less than A, then we'll end up with two triangles. Are possible. If that is the case, what do we do? Well, all we need to do is use the law of sines, and if we use the law of sines, what it's going to do is tell us the case where this happens. So we could use the law of sines here using sine B over B equals sine A over A, and we could figure out this angle, and we could figure out whatever that angle is. If we then we could calculate this length, and that would be easy, just a simple application of the law of sines. If we then look at this, you'll notice, if we just focus on the triangle formed by these two red angles and this, it would mean that this angle A and this angle over here would have to be the same, because that triangle, so this angle here, this angle right here, this angle right here, and this angle right here would have to be the same, because these two sides are congruent. What does that mean? This angle, because it's isosceles, are congruent, which means that this angle right here in our second case would be 180 minus whatever angle A is. So then that means we could use the law of sines again. We calculate using the larger triangle using the law of sines, and then once we get this angle measure, we can figure out the angle in the obtuse triangle that ends up covering the other case, and then use the law of sines to complete it. Hopefully that has helped clarify how you can identify when there's two cases, when the value for this second leg, right, second side of the triangle, is between the H, that's the height, the perpendicular distance, and the height of the side length that's adjacent to the given angle. So that is between H and A.